Dear students, welcome to Eazy Btech, your guide for Btech and beyond. Our subject signals and systems. And today's session, we are going to see in today's session classification of signals, very important topic. Okay, and you please subscribe, share the channel to your friends. It is very helpful to you to understand Btech subjects very easily. Let's start our session classification of signals. Classification of signals. Very important topic, classification of signals. First we will write the classification list, then we see one by one. Classification of signals. Classification of signals. The first one, continuous time and discrete time signals. Continuous time and discrete time signals. Discrete time signals. And the second one, even and odd signals. We have even signals, we have odd signals. Even and odd signals. The third one, periodic and aperiodic signals. We have periodic signals, we have aperiodic signals. Periodic and aperiodic signals. Aperiodic signals. And fourth one, energy and power signals. Energy and power signals. Power signals. And fifth one, causal and non-causal signals. Causal and non-causal signals. Non-causal signals. And the sixth one, deterministic and random signals. Deterministic and random signals. Random signals. So we'll see one by one. Continuous time and discrete time signals. So this is the classification of signals. Let's go to first one, continuous time and discrete time signals. This already we have seen at the beginning of our subject. Again we discuss continuous time and discrete time signals. Continuous time and discrete time signals. Discrete time signals. First I will give you example, continuous time signal example. Discrete time. So here in continuous time signal, the x-axis is a small t, continuous time. In discrete time signals, the x-axis is small n. And discrete time signals are represented as like x of n, small n. And continuous time signals are represented as like x of t, small t. And this continuous time signals defined for every value of time. For every instant of time, the signal is present. If you take t equal 0.001, the signal is present. 0.002 signal is present. 0.1 signal is present, and so on. That is continuous time signal. If you come to discrete time signal, they are defined only at integer values of time. So integer value n is 0, the signal we have 1, and n is 1, the signal or amplitude we may have, or it may be 1.5, and at next integer value 2 the signal will be -1, and integer value 3 the signal is, for example, 2. So only discrete intervals 0, 1, 2, 3 we have signal, or it is defined. So in a simple manner, amplitude and time both are continuous. Continuous time signal means amplitude and time both continuous. Both are continuous. Continuous means any value we can take. Amplitude can be any value, time can be any value. And discrete time signal means amplitude is continuous but time is discrete, integer value. Amplitude is continuous, any value, but time must be discrete. It must be discrete. Right? See here time. N is 0, n is 1, n is 2, n is 3. Discrete time or integer values. Okay? Next, we go to another classification. Even and odd signals. Even and odd signals. Even we can also call symmetric signals. Symmetric or even signals. Odd signal is also called asymmetric. They are asymmetric signals. Okay? And if you see the example, even signal, odd signal, I am taking a rectangular pulse. It is between -2 +2. This is t, and this is a given signal x of t. The amplitude is 3. The amplitude of the signal is 3. Now, odd signal, if you see example, this is odd signal example. Okay? X-axis t, and odd signals passes through origin. The given signal is x of t. Here you can take amplitude 2, here amplitude -2, here +1, -1. So examples are given. Now come to definition. What is the definition of even signal? X of -t means time reversal of x of t is equal to again x of t. X of -t is again x of t for all values of t. For all t. For all the time. Similarly, here in odd, x of -t is equal to minus of x of t for all t. For all t. We can check by the definition. For example, you take t is equal to 1. At t is 1. What is the value of the signal? 3. And similarly check at -1. T is 1. So minus t means -1 now. What is the amplitude? Again 3. So 3 is equal to 3. Same. So for every time, x of -t and x of t must be same. Then it is even signal. It is an even signal. And another example, I can draw even signal. This is also even function. This is also even function, right? So they are like this, x of minus t equal to x of t, even signal. Now odd signal. See odd signal, you take t is equal to 1 for example. At t is equal to 1, we have value 2. At t is minus 1, at t is minus 1, we have value minus 2. Opposite or not? Here 2, here minus 2, opposite. And they must be 0 at t is equal to 0. Odd signal or odd function is 0 at t is 0. So this is the point. Odd function or odd signal is equal to 0 at t is equal to 0. In the similar discussion, in the similar way, discrete time signals. If you take discrete time signal, what is the even signal and odd signal definition? Even signal is x of minus n equal to x of n for all n. For all n. This is even signal. If you take odd signal, x of minus n is equal to minus of x of n for all n. For all n. And see example here. Even signal, odd signal. Suppose n equal to 0, we have signal 1, and n is 1, we have 1.5. Similarly, at minus 1, it must be 1.5. At a 2, this is equal to, the signal is like 2, you can take 2. At minus 2 also, it must be 2. Right or not? Condition is satisfied. Right? This is even function or even signal. Now odd signal. The amplitude must be opposite. Amplitude must be opposite. At n equal to 0, the signal is 0. At n equal to 1, if you take 1, at n is minus 1, the amplitude is reverse minus 1. At n equal to 2, we are taking signal 1.5. At n is equal to minus 2, it must be minus 1.5, opposite. This is even odd signals. Next, one more important point about even and odd signal. Any signal, any function or any signal, like x of t is a continuous time signal, we can write like this: even part plus odd part. Any signal, we can write sum of even part and odd part. This is called even part of the signal, and x of t is odd part of the signal. Now how to get even part and odd part of the signal? X of t even part, that is xe of t. To get the even part, so do this: x of t plus x of minus t by 2. X of t plus x of minus t by 2. X of t is the signal, x of minus t, folding or time reversal of x of t and do by 2. You get even part. To get the odd part of the signal, x of t minus x of minus t by 2. Okay, and if you sum these two, if you add these two, even part and odd part, we get the actual signal x of t. In similar manner or in similar way, we can do discrete time signals also. For discrete time, signal x of n, we can write even part and odd part. To get the even part, odd part, in the same way, x of n plus x of minus n by 2 we have to do. And to get the odd part, x of n minus x of minus n by 2. So this is another point related to even and odd signals. And one more important point, suppose if you have integration minus a to a x of t dt, this integral value, here x of t is a even function. So this integration we can write as 2 into 0 to a x of t dt. Suppose odd function, x of t is an odd function. Then what happened to integration minus a to a x of t dt, which is a odd function, x of t is odd function, then this integral is equal to 0. So very, very important, remember. Okay, even and odd functions. Next, see periodic and aperiodic signals. Periodic and aperiodic signals. Periodic and aperiodic signals. I just give you example, periodic and aperiodic. So this is up to infinity. The signal repeat itself up to infinity, up to minus infinity. Suppose this is 0, this is pi, this is 2 pi, x-axis t, minus pi, minus 2 pi, up and so on. So the amplitude of the signal is A. This is a periodic signal, x of t. Aperiodic signal means it will not repeat itself. It occurs or it appears only once between minus infinite and plus infinite. It appears only once between minus infinity to plus infinity. So let's take example. Aperiodic signal. This is aperiodic signal. It is not repeating. This shape is not repeating. That is why it is aperiodic. Only once it is appearing. So amplitude is, for example, 4. So this is aperiodic signal. And this is periodic signal. So we have a definition. What is the definition? X of t plus capital T is equal to x of t. X of t plus capital T is equal to x of t. Then it will become periodic. Otherwise, aperiodic. Otherwise means x of t plus capital T is not equal to x of t. Means after capital T, the same signal has to repeat. The same signal has to come or it repeats. So here capital T is called fundamental time period. Capital T is called fundamental time period. What is fundamental time period? The minimum time at which minimum time at which the signal is repeating itself, at which the signal is repeating itself. The signal is repeating itself. That is called fundamental time period. If you go to example, our example, so this is the signal, sawtooth signal. So 0 to pi. Again from pi onwards, the same signal is repeating. Again pi means 2 pi. The same signal is repeating. So the minimum time at which the signal is repeating itself is called fundamental time period, or we can say the time taken by the signal to complete one full cycle. How much time it is taking to complete one full cycle. This is the one full cycle. This is one full cycle. How much time it is taking? That is called time period of the signal. So here in this example, how much time it is taking to complete one full cycle? 0 to pi is the cycle. How much time? Pi is the time period. T is equal to pi. So for every pi, the signal comes. So 0 to pi, we have one full cycle. Again from pi to 2 pi, one full cycle every pi. So this is time period. T is equal to pi. Okay. And here we have one more relation. Omega is equal to angular frequency, omega or omega naught, 2 pi into f. What is f? Frequency in H. So frequency in H we get 1 by t. Time and frequency reciprocal or inversely proportional. So omega naught is angular frequency, which is equal to 2 pi f, and f is the frequency in H, 1 by t. Right? Then omega naught we can write like 2 pi by capital T. 2 pi by capital T. Okay? Here radians per second. So this is about periodic and aperiodic signals. Similarly, in case of discrete time, if you take discrete time signal x of n, so how can we define periodic or not? This is the way. X of small n plus capital N is equal to against x of n. So after capital N, the same signal is repeating. So here n is called time period. N is called time period. It must be integer. This is very, very important. The capital N must be integer value, because discrete time signal, x of n is a discrete time signal, so capital N must be integer value. Please remember this point. Otherwise, if x of n plus capital N is not equal to x of n, then it will become aperiodic. Is not equal to x of n, then it will be aperiodic. It will be aperiodic. Okay. So this is about periodic and aperiodic signals. Now I have an example. What is that example is? X of t is equal to sine 3 sine 5 pi t. 3 sine 5 pi t. What is the time period of this given signal? What is the time period of this given signal? If you have the point is here, what is the point is? If the signal is a sinusoidal, Sinusoidal means like sin omega naught t or cos omega naught t. If it is sinusoidal, the time period of sinusoidal is 2 pi by omega naught. 2 pi by omega naught. Here you see omega naught, that you can write 2 pi by omega naught. It will give you time period. And similarly, suppose if you have complex exponential like e power j omega naught t, your x of t is e power j omega naught t. What is the time period? Same manner, 2 pi by omega naught. Here whatever the omega naught, that you write by omega naught, 2 pi by omega naught. So here the given signal 3 sine phi pi t. What is omega naught here? This is the omega naught. So what is the time period? Simply time period t is equal to 2 pi divided by 5 pi. So 2 by 5 seconds. Okay. Another example, suppose here e power j pi t. What is the time period? 2 pi by omega naught. What is omega naught here? Omega naught is pi. So 2 pi by pi, it is equal to 2 seconds. So for every 2 seconds, the signal repeats. Okay, for every 2 by 5 seconds, the signal repeats. That is the meaning of time period. Okay, right? Now one more example. If you have discrete sinusoidal means x of n is equal to like 3 sine 2 pi by phi n. 2 pi by phi n. So what is the time period of this? So time period capital N is equal to 2 pi by omega naught into small m. M is any integer, one positive integer, 1, 2, 3 and so on. So using m, we can make capital N also integer. The minimum value of m we take, then capital N must be integer. I told you discrete time, the period capital N must be integer. So here discrete sinusoidals. What is discrete sinusoidal? We have sine omega naught n. Sine omega naught n. This is the discrete sinusoidal. What is the omega naught he given? 2 pi by 5. Compare. We can understand omega naught. 2 pi by 5. Now capital N is equal to 2 pi by omega naught is 2 pi by 5 into m. So you get 5, 2 pi cancel, 5m. So we can take m 1. So it will be 5. 5 samples. What is 5 here? Samples. So this is a way of doing time period. Another example. Here n is capital N must be integer. That is the point. For example, if you take cos 3n, do it. What is capital N? 2 pi by omega naught into m. Okay. Now, in the place of omega naught, we have 3. So 2 pi by 3 into m. So by taking m value 1 or 2 or 3, is it possible to make capital N is integer? Can you get n value? Capital N is integer by taking n is 1, n is 2, n is 3. Suppose if you take n is 3, 3 get cancelled, 2 pi. 2 pi is not an integer. So what do you understand by this? Capital N is, in this case, we are not getting integer. So the given signal is a periodic signal. The given signal is a periodic signal. This is a clarity I am giving you. And if you have like x of n is equal to e power j omega naught n, e power j omega naught n. So what about this? The same. N must be like 2 pi by omega naught into m. Okay, the capital N means time period. The total value must be integer. Then only the given signal will become periodic. The capital N must be integer. Then the signal will become periodic. This is the point. Remember. Okay. So we stop here. We have continuation of classification of signals in the next session. Thank you. Thank you all.